was considered a supernatural phenomenon and worshipped as a god in a number of ancient civilizations. In Egypt, it was worshipped as Ammon, in Mesopotamia as Samas, and in Greece as Apollo. The Greek philosopher Anaxagoras offered the first scientific explanation in the 5th century BC. In his view, the sun was a glowing, hot iron sphere. This unusual idea was considered blasphemous, and he was imprisoned for his views. After constructing his telescope, Galileo Galilei also studied the sun and discovered sunspots. Later, Isaac Newton used a prism to split white light from the sun into its components. Still later, William Herschel used this method when he discovered infrared radiation around 1800. In his experiments in the 19th century, Joseph von Fraunhofer was the first to observe absorption lines in the solar spectrum, from which the chemical composition of the atmosphere could be determined. Hans Bethe developed the theory of nuclear fusion in 1939, which explains how energy is generated inside the sun. The first space probes sent to observe the sun were NASA's Pioneer probes in 1959 and 1968. Orbiting the sun at a distance equal to the Earth's, they thoroughly examined solar wind and explored the sun's magnetic field. The U.S. West German space probe Helios, launched in 1974, conducted research from within Mercury's orbit. The sun's X-ray radiation was examined by a space telescope from the Skylab space station. After escaping the planet's orbital plane, the Ulysses space probe studied the sun, providing a great deal of new information about its polar regions. SOHO is one of the most important probes to research the sun, always positioned between the sun and the Earth. It has been taking pictures of the sun since 1995 in both the visible and ultraviolet ranges. Recently, several new probes have been examining our star, which is very important as solar activity has a profound influence on our weather. Utilizing the energy of sunlight is gradually becoming more widespread. It is used for producing electricity by solar panels and solar power stations, and for producing heat by solar collectors. The sun is an average star, a yellow dwarf. At 4.6 billion years old, it is now roughly halfway through its lifespan of about 12 billion years. It is composed of nearly 3/4 hydrogen, which is converted into helium by nuclear fusion in the sun's core, thereby producing energy, high-energy photons. When its fuel supply is exhausted, it will shrink, and its core will heat up sufficiently for the helium to convert into carbon.
This process will result in even greater energy production. Therefore, the star will expand to several hundred times its current size, so the Earth will probably be swallowed up.
However, the sun's surface will be less hot, and it will become a red giant. This phase will not last long. When the fusion stops, the sun's internal pressure will decrease, and it will collapse due to its own gravity. It will then become an Earth-size, extremely dense white dwarf, and will cool down after billions of years. The sun is not made up of solid material. It consists of plasma. This is why belts of different latitudes rotate at different rates. Its equatorial areas rotate every 25 days, while polar areas only rotate every 32 days. Its atmosphere is layered, made up of the photosphere, chromosphere, and corona, and it gradually merges into the interplanetary medium. The corona becomes visible during solar eclipses. 98.87% of the mass of the solar system is concentrated in its central star. The sun has an enormous mass, so it has very strong gravity, which holds the solar system together and governs the movement of all the planets and smaller objects in it. The sun emits a large amount of energy, mainly in the form of ultraviolet, visible, and infrared radiation. But there is also a small amount of other types of radiation, like gamma rays, X-rays, and radio waves. Elementary particles, mainly protons and electrons, are also ejected from the sun. These make up the solar wind. The core of the Sun has an estimated temperature of 14 to 15 million degrees Kelvin, a pressure of 3 times 10 to the 11th power atmospheres, and a density of 155 grams per cubic centimeter. The core extends from the center to about 1/4 of the solar radius, and it works as a nuclear reactor, where energy is released in the form of high-energy photons, gamma rays, and X-rays during the fusion of light elements into heavier ones. The fusion process involves the fusion of the nuclei of deuterium and tritium, both isotopes of hydrogen. Deuterium nuclei consist of 1 proton and 1 neutron, while tritium nuclei are made up of 1 proton and 2 neutrons. The reaction produces a helium nucleus consisting of 2 protons and 2 neutrons. The reaction releases 1 neutron as well as energy in the form of free photons. During the collision, the forces of repulsion in the protons must be overcome. This is only possible if the hydrogen atoms move very fast, that is, if the temperature is extremely high. The Sun can keep up the current level of radiation for another 6 or 7 billion years more. The core is surrounded by the radiative zone, which extends to about 70% of the Sun's radius. Photons often collide, become absorbed, and are then emitted in this zone. It very often takes up to 10,000 years for the photons to reach the surface. Large-scale convection takes place in the outer zone of the Sun, which takes up about 25 to 30% of the solar radius. This layer is therefore called the convective zone. Heat is transmitted to the photosphere by the flow of the zone's material. It is then emitted into outer space. The Sun's atmosphere is mainly composed of lighter chemical elements, 71% hydrogen, 27% helium, and 2% heavier elements. The nucleus contains 35% hydrogen.